So, okay, so I wanted to talk about this idea that dynamical heterogeneity might have something to do with fluctuations in the time variable. So, okay, I guess most of you know what dynamical heterogeneities are. Just do a very quick reminder. The idea is that people believe that in glasses or in liquids near the glass transition, the system basically has regions where the relaxation is happening at different rates, and this has lots of consequences. For example, the non-exponential relaxation, the decoupling between viscosity and diffusion, and this actually has been directly observed in experiments where people do particle tracking. And there are many other experiments which are also microscopic in a sense, but a little bit less direct. So, yes?
Maybe it's a matter of semantics, but I'm not sure you can say you have regions that relax at different rates. When you have regions that decorrelate fast in a given experiment, and some that decorrelate slow. But to talk about a rate, you have to do many repeated experiments.
Okay.
If you do many repeated experiments, you will not see regions that are always.
Right. So these are thermal fluctuations, right? So this is not like
it's just the use of the word rate.
Yeah. So I mean, many people describe it like that. So yes. Okay. So you could say it in a different way. Essentially, what you are saying is that the relaxation is happening in different ways in different regions. And actually, I mean, as I said before, this is used to explain, for example, the non-exponential relaxation. And the idea, for example, in the case of the non-exponential relaxation is if you have some relaxation function that goes like maybe a stretch exponential, you can always decompose this as a sum over some spectrum of relaxation times of exponential relaxations. And then here you have the weight for the different relaxation times. And what people have argued for many years is that, well, maybe this weight that we have here in this sum has to do with how often I find this relaxation time spatially. So I think that that's the reason why people sometimes describe it this way. But anyway, I mean, in any case, we have these very strongly correlated fluctuations here in the system. And what I want to do is present an idea of how this might be happening. So the idea is the following, and I'm going to first present the idea and then give you some ways in which this could actually be tested. And for the moment, I'm going to ask you to suspend your disbelief, and maybe later I'm going to come back and say, well, why on earth would you think of believing that this might be happening? Okay? So the idea is the following, that basically if you look at how different regions in the system relax, so let's say you look at some coordinates that describe some regions A, B, and C. Okay, then what we are postulating is that all these regions have essentially the same relaxation trajectory. These drawings are not identical, but let's say I managed to draw them identically. But in different regions, the system has advanced more or less along this same trajectory. Okay? So if you want to put it in a little bit more quantitative way, basically what one tries to do to describe the relaxation in the system, it would be the following. One very common way is to say, well, we look at the correlation between the states of the system at times t and t prime, okay? And we use this as our way of describing how the relaxation is happening. So one way, for example, if our system was a spin glass, we can define our C of t prime to be the sum over space of the values of the individual spins at times t and t prime. Basically, is the overlap of the spin configuration. And then you have to think about how you are going to average this and so on. So what I propose to do is to say, well, yes?
So this figure depends on the quality you have in mind, because different qualities may have different graphic description.
Right, so I'm going to go back to that in probably 10 or 15 minutes. Yes. So, so for example, in a spin glass, I could have something like this. In a structural glass, I may be using the intermediate scattering function. Let's take just the real part of the intermediate scattering function. Okay, so what I'm saying is the following. Instead of just taking these global measures of how the system is relaxing, let's look at these things locally. In some coarse-grained regions. So you divide your system in regions, right? And you look at correlations here, here, and so on and so forth. Okay? So instead of having the sum over the whole system, now your correlation will be something like 1 over the number of degrees of freedom, let's say the particles or the spins or whatever, in some box around point R, and then sum over your particles, let's say, in the region R, in the region around R of whatever the quantity was, for example, this cosine here. So basically what we are saying then is actually that this is the starting point, is to say, well, okay, so this is now going to be a correlation, which is a local quantity, it's a coarse-grained quantity. And what we are going to say is that this quantity, which is going to be fluctuating in space, is going to be fluctuating in a very particular way, which is the following. So basically what we say is we obtain the local correlation by replacing the time variable in the global correlation by some fluctuating quantity. Right? I replace my t by some other quantity, which is not quite t. Okay? But now I take my global correlation and I say, well, most of the fluctuation in my global correlation is going to be described by this. So that's basically the postulate. Okay, so so going back to your question for just a moment, basically you would do this. The function C that would appear here will be different depending on exactly what is it that you are using as your two-time correlation in principle. But let's say, well, okay, how can we...
The function h depends on what variable you are looking at, what quantity you are looking at, or would the function h be the same for every type of correlation function you can...
Right, so, okay, so this has been checked a little bit, and the answer so far is no.
You're going to tell us what h is.
H is some fluctuating quantity.
So the answer would be you need a different h for every correlation function that you want to look at, or?
No. The answer is you have the same h.
Same. Okay.
Right. Okay. So so how would you test for something like this?
Can I ask one more question?
Yeah, sure.
I would imagine that h depends on the scale on which you block things, right?
Right. So
anyhow clear how this would depend on the size of these blocks?
So this, and I'm going to jump ahead of myself. This has to do with the presence of a Goldstone mode. So you have to actually coarse grain on a relatively large region in order for this kind of fluctuations to dominate. Okay, and I'm going to actually show results that show you that very clearly. Okay, so how could I test for this idea? So one way I could do this is the following. Let's say I take 3 times. Okay, and I take the correlations between the state of the system at these different times. Okay, and I plot one against the other.
This is now the global correlation?
The global correlation, yes. Let's not get lost here. Okay, so what do we expect? Well, if this time t2 is very close to the time t3, then this correlation is going to be rather large, and this correlation between these two is going to be rather small, right? If we have something like this correlation is going to be small, this one is going to be large, so I'm going to be around here. If I go to the opposite case, where t2 is close to t1, I'm going to have a point more or less there. And I'm going to have things in between. Okay?
So you fix T1 and T3 and you vary T2.
And you allow T2 to vary. Okay? So one could say, well, okay, so what happens if I now look at my local fluctuations? Okay? So let me do this naively, very naively first. If I look at my local fluctuations are going to be associated with fluctuations of the time variable. So I would expect that if I only allow T2 to fluctuate, then basically if my global correlation is here, okay, let's say this is the point given by C of T2, T3, and C of T1, T2. If I now look at local correlations, what I would expect is that they will be spread out along this curve. Because basically what would be happening is that the T2 variable will be fluctuating, okay, as you allow the T2 variable to fluctuate. What you have is you have points that go along this curve. and you don't have any points that go away from the curve. Of course, that has a big problem. The big problem is why do you allow T2 to fluctuate and not T1 and T3? So that's what I'm going to deal with next. Okay, so in principle, if by some miracle I managed to pin the fluctuation so that only this was the variable that was fluctuating, I could recognize that by looking at these local quantities and seeing that they fall along this curve. So then let's say, okay, I don't have that miracle, but I have a system which is nice. So let's consider a situation where we have a correlation between times t and t prime, which is a power law. Okay? So you can find this as an approximation, a reasonably good approximation in simulations of a 3D Edwards-Anderson spin glass.
Excuse me.
Yes?
Is it some assumption about a time scale separation, namely that you may have some very fast fluctuations perpendicular, but they somehow
right. So
out, and you're considering only fluctuations around this scale?
That goes to his question also. Okay, so what we are interested in here is really the slow part of the relaxation. So a big assumption here. So the big assumption here is that we have a separation of time scales. And that what we are really looking at is the alpha relaxation. If you have a two-step relaxation, we are looking at the second step of the relaxation. Okay, we are not looking at the fast processes. Okay, and even here, for example, I'm going to show later. I'm going to show some data, and the data start at a correlation which is clearly below 1. They start at 0.8 or whatever, which is where you have a plateau in this two-time correlation. Okay.
I just want to make sure. T2 is not actually fluctuating, right? I mean, you fix T2, but then
right.
You say locally something has either relaxed before T2 or it relaxes after T2. And,
right.
And that's why it falls on that.
Right. So the only point here is that what we are saying is these things, instead of relaxing like this or like this, right? Instead of going this way or going this way, they go the same way, but they do it before or after. That's the only thing we are saying.
You're assuming that.
Right. Well, that's the proposal, okay, and that's what that's what we test with simulations, and that's what we motivate with some calculations also, okay. So anyway, let's say we have this. Then in this case, we can say, okay, T1 over T3 is equal to T1 over T2 times T2 over T3. So T1 over T3 to the power minus gamma is T1 over T2 to the power minus gamma, T2 over T3 to the power minus gamma, which means that now I have a triangular relation between the correlations, and now I can write the following. I can write that 1 is equal to the correlation between 1 and 2 divided by the square root of Q Edwards-Anderson C13 times C23 divided by the square root of Q EA times C13. Okay? So because of the fact that I had a particularly simple form for my correlation, then I can find a way of getting rid of the influence of C13. Now I have these two quantities. I call this X and I call this Y. which I can plot like this. And now, no matter what T1 and T3 are, so in principle, here, if, for example, let's say I repeat the same plot, but I take T1 and T3 closer to each other, what's going to happen is that all my correlations are going to tend to be larger. So instead of having a curve like this that extends between low values of the correlation and high values of the correlation, I will have a shorter curve where the correlation can go between an intermediate value and a relatively large value. It doesn't go so low as it goes here. Okay, so in principle, by varying T1 and T3, what happens is I'm moving and I have different curves like this. Okay? Now, if I actually do this rescaling, what that does is that I compress this back. So if this was C23 and this was C12, but now I plot these quantities x and y, what happens is by dividing by the square root of C13, I go back to having just one curve, no matter what T1, T2, and T3 are. Okay? And again, this approximation is only valid for the actual long time decay of the correlation. Okay? Okay, so if we have this, then it's not going to be that easy to interpret the points here, but it's clear that if you are separating T2 from T3, you are going to be moving in this direction. So, and the other thing is, no matter what you do with your times, your points are always going to fall along this curve. Yes?
Suppose I have some landscape with a metastable minima.
Yes.
The system goes in principle from some initial state to the deepest or deep.
Mm-hmm.
Now, so you will have some trajectory, but in principle you can think of some excursions which would go and visit some other metastable minima.
Right.
So this assumption that there is essentially one-dimensional trajectory over which you can go faster or slower, seems intuitively to contradict this picture that you can.
Right. So one thing I could say there is that when people try to think about this kind of picture, they try to say, well, I'm not going to be working with a system which is much larger than maybe 50 or 100 particles, right? So basically, once you coarse grain to that level, basically what you have is more or less one trajectory. That would be what would emerge from here. Now, how do you understand that in detail in terms of that picture? I wouldn't know. And it's really a good question.
It didn't seem to answer his question.
Was that?
It didn't seem to answer his question, did it?
What do you mean?
If you have, no matter what size of coarse graining you've got, you can have activated processes that don't seem to follow the schemes. Is that what you were thinking of?
I was thinking about making some excursion towards other and being trapped there for a million years before you.
I don't see how that has to do with what size coarse graining you're using. But maybe it does.
I mean, the landscape picture, you cannot really go much further away, right? You have to look at a relatively small region, right? Because beyond some distance, you have uncorrelated events. You have things happening completely independently, right? So the question would be, okay, can we look at what happens in a region of the order of 50 or 100 particles and see that things are doing something similar to this?
I think you should go on and
okay.
That's what you find.
Okay. So, okay. Anyway, so if we have a simple form for this correlation, then we will have something like this. And again, the expectation will be if if the fluctuations are given by something like this, then we would expect that if we have the global, this is our global correlations. This is our global pair XY, and now we would have our XR, YR at different points falling along this curve. Okay, that would be the idea. Okay, so when should this fail? For sure. So one thing that could happen is, well, maybe we are saying something that is completely trivial. So one thing that we would expect is that this actually happens, is only present at low temperatures and long times. Why do I say long times? Well, this has to do with separation of time scales. So I'm looking at the alpha relaxation and I'm looking at very long times. So, and the other thing is that what we are trying to do is we are trying to describe these correlated fluctuations. So if we coarse grain, so if the coarse graining region is too small, basically this should fail. It should fail because you have a lot of other fluctuations which have nothing to do with this. Okay? So, anyway, so let me show you something then. Okay.
Something to pull the screen down.
Oh, yes.
Is the length of the time over which this is supposed to work depend on the temperature? It probably does, I'm sure.
Yes. So I'm about to show exactly that. So okay, so what I'm showing here is the result of several simulations. So so here we have several systems. What we have, these two systems here are short polymers with 10 monomers each. A has Lennard-Jones interactions, B has WCA interactions, just the repulsive part of the interaction. C and D are particles, C with Lennard-Jones interaction, D with WCA interactions. These are binary systems, so to avoid crystallization. And then the same system that we have here, so all of these systems are below the mode coupling critical temperature. I mean, this simply is for the reason that we are looking at the aging regime. The system is out of equilibrium. They are not very far from the last transition. They are maybe around 10% below the mode coupling critical temperature. And then these systems, the system, the one that is marked in light blue, the temperature is around 10% above the mode coupling critical temperature, and the one that is in light green is around 50% above the mode coupling critical temperature. And what we show here is basically that curve, x versus y, where this function phi is not exactly the two-time correlation, but we have to actually take into account the fact that the two-time correlation does not have that form. And what we did was we did so I have to go back for a second to the blackboard. So what we did was the following. We found a way of fitting the two-time correlation as some function f of h of t divided by h of t prime, where the f is a stretch exponential. So what we have here is Q Edwards-Anderson, well, QE or whatever, exponential of minus the logarithm of h of t divided by h of t prime to some power beta. So what we do is...
You're not going to say what h of t is now?
Okay, so the h of t, we need to take different forms. So this is the global h of t. So here are the forms. Okay, if the system is in equilibrium, you just take the h of t to be an exponential, and that gives you time translation invariance, right? You have exponential of t divided by exponential of t prime. That's exponential of t minus t prime. You take the logarithm, and you recover the usual stretch exponential. Then if you have aging, what we have done is we have used these two forms to, where is the other one? Here. We have used these two forms to do the fits. And basically what this had to do with was the fact that these systems, so again, we looked at the systems while they were aging, and some of them had what's sometimes called superaging, where the relaxation time was growing faster than the waiting time, like in this system here, and other systems where had the relaxation time growing slower than the waiting time, like in the usual binary Lennard-Jones system that many people here have worked with. There you get that the relaxation time goes more or less like the waiting time to the power 0.9. So depending on the time evolution of the different systems, you need to take different you need to take different functions h of t, okay, and then the stretch exponential the quantities that enter into this stretch exponential fit are pretty standard. I mean, beta is of the order of 0.6 more or less. The QEA is around 0.7 or 0.8. It's all very reasonable. So the only role that this plays is that this allows us to go back to a ratio between two quantities that we can interpret as times, or in this case as reparametrized times. So basically, if we apply the inverse function of f to this correlation here, so we define this phi of tt prime, if you want, as f to the minus 1 of c of tt prime, then this f to the minus 1 gives us h of t divided by h of t prime. And then we are back where we were here, where we can get rid of the dependence on t1 and t3 and collapse everything into just one curve. So this is the global data, and this is just a preparation to actually see what happens. I mean, the only point here is to be able to put all the data. So these are all the data for all these systems in the Asian and in the equilibrium regime for those of... So for example, here, these two systems that we have simulated at temperature higher than the mode coupling critical temperature, we have taken data here in the region where the system is clearly aging, and then here in the region where the system is clearly in equilibrium. Same for this one. And we treat those as two separate data sets, and we need to take different functions h for each one of those. And the point here is simply to have this line that describes where the system is for all times, and be able to see if the fluctuations occur along this line or perpendicular to the line. That's what we want to look at.
In what you did in the board, h was a local function, right? Depended on the...
Right, so this is a different story, and maybe using the same letter is a bit confusing, but
different functions.
These are different functions. So this is simply something that we use. For the moment, this is something that we use to try to describe the correlation in your system. That's it.
Yeah. There's nothing to do with this h sub r that you use.
Right, right. So but the thing is going to be that when you look at the local values, what you are going to expect is simply that this h of t is replaced by an hr of t, which is not going to have these forms that we wrote there. It's going to be some fluctuating quantity. Okay. So what we do next is we go and try to check if what we were predicting is happening. So
may I ask, why are you not looking at coarse-grained quantities when you have all the data in your simulation?
Right.
Much more convincing if you would actually look at coarse-grained data and see whether different...
That's what I'm going to show now.
Okay, good.
So
this could come from others.
Oh yeah. This is just fitting. I'm just saying I look for a way of fitting my correlation and see what happens. So now let me show you this. So these are my 8 data sets, and I'm going to turn off the light here. Okay. So what am I doing here? So for example, let's just focus on this one here. Okay. What I'm doing is the following. I have my variable x and y. The red points here correspond to the global values. Okay, so as I change the times T1, T2, and T3, and I calculate the global quantities x and y, I get all these red points along this curve, which this curve is superposes almost exactly with the hyperbola 1 equals xy. Okay, now what I do is the following. I choose one set of times T1, T2, and T3, so that my x is very close to 1 and my y is very close to 1 here. Okay? My global x and y are very close to 1. And then what I do is the following. I divide my system in regions. I do exactly what you proposed. Divide my system in regions, calculate x and y for each region, and then I plot a probability distribution, a joint probability distribution for my x and y of that region. That gives me these contour curves that I have here. So the smallest one corresponds to enclosing 25% of the probability, 50% of the probability for this one, and 75% of the probability for this one. So this is one of the systems which is at a relatively low temperature. And at least what I would say here is that I see much more fluctuation along the curve than I see away from the curve. That's what I was expecting. Okay, so I was expecting that most of the fluctuation is going to happen along this curve. Then I can repeat the same procedure for other global values of x and y. Okay, I take a value of x and y which is around here. For the same times, I obtain the probability distribution of the coarse-grained quantities xr and yr. I get this probability distribution. I look at this smallest of the contours, which is basically giving me the most likely fluctuations, okay? And I see that it is more or less elongated along the curve. The other thing that I observe is that when I take the larger and larger contours, they are not so aligned along the curve. So you have more rare fluctuations, which are actually moving more away from the curve. The other thing I can see is I look at all the systems that are at around 10% temperature below the mode coupling critical temperature. And they all look very similar to each other. I mean, if someone cut each one of these plots and erased these letters here and tried and showed it to me, I couldn't tell which one is which one, really. So they are very similar. And now, what happens if we increase the temperature? So when we increase the temperature, here, this is the data for temperatures 10% above the mode coupling critical temperature. What we see is that the fluctuations away from the curve are a bit stronger than they were here, although I would say that there is still some anisotropy along the curve. Okay? And here, since we can equilibrate the system, we can actually compare the system which is equilibrated here and the system which is still aging, which is here. In all cases, we try to take the times as late as possible, compatible with the data set we are looking at and compatible with the quantities X and Y that we are measuring. So it looks similar, although there are obviously some minor differences, but at least the geometry of the regions looks very similar. If we go higher in temperature, and this goes back to your question about how much data you are going to find, for example, this system where we have the temperature 50% above the mode coupling critical temperature, we have fewer global data here simply because the system equilibrates faster. Okay, so in the aging regime, we don't have so many data, but still we notice that it is fluctuating much more in this direction. And again, it looks more or less similar if we look at it in equilibrium or in the aging regime. So, how am I this time?
You have 15 minutes until you've been an hour, but you can, we're flexible.
Okay. So one thing we could do is to actually compare in more detail here. And okay, so what am I showing here? I'm showing the 25% contours for all my systems, and what you see here is the following. So here we have the systems A, B, C, and D, which all of them give me these ellipses that look pretty similar. The points that are shown here correspond to the global values of the correlations, the global values of X and Y, which are not quite exactly along the curve because our fitting is not perfect. So all of those give you the fluctuations which are most oriented along this line. Now, if we look, for example, at systems, let's see, at E, what you have is this curve here, the dark green, okay? So the dark green, you see clearly that you have a little bit more fluctuation away from this curve, okay? And also the dark green is shorter along the curve. It ends here and here. It's shorter than the other ellipses that we see. And then if we go to this other case, which is 50% above the mode coupling critical temperature, we have even more fluctuation away from this line and even narrower in this direction. Well, not so narrower, really, but you have more fluctuation in this perpendicular direction. Okay, so you notice immediately that as you increase the temperature, the fluctuations increase in this perpendicular direction. The other thing one can look at is the following. This is supposed to be a property that is an asymptotic property for long times. So actually it should fail if you don't take the times long enough. And that's what we did in the curve which is labeled as B prime. So B prime, which is this light blue that you can see here, okay? In that curve, what we did is we took the times roughly 2 orders of magnitude shorter than the maximum we could take them, okay? And the result you can notice is if you compare with B, which is here, which is this brown curve here, okay? The B prime has clearly more fluctuations in the direction perpendicular to the line. So you have more fluctuations that cannot be explained by time reparametrization invariance. So, so basically what we are saying is, well, we really need the long time limit. And the other thing is going back to the coarse graining. Now, all the data I have shown are data where the coarse graining is done choosing the size so that on average each region would have 125 particles. So now what I do is the following. I take a much smaller region with 23 particles, and I look at the fluctuations for that smaller region, and I get this probability distribution, which is, okay, the fluctuations are much larger. That's not a big surprise because you are averaging much less. But the important thing here is that this curve, B second, is done exactly at the same times with the same global correlations as B. The only difference between B and B second is the coarse graining, nothing else. Okay, how big did you take your region to do the coarse graining? And you see that clearly that here you have a lot of fluctuation in the perpendicular direction. I would say that you have more fluctuation in the perpendicular direction compared to what you have along the line. So, in summary, we expect that this should be a description of correlations which are fluctuated over relatively larger regions, and we see that by changing the coarse graining. We expect that this should be something that happens when you take the times as long as possible, and we see that if we actually reduce the times, we lose the anisotropy that we were expecting. And also, as you reduce the temperature, you expect this to be this effect to be more noticeable. And this is simply because as you reduce the temperature, you can allow the system to evolve for a longer time, because basically when the relaxation time plays the role of a cutoff here. Okay, so that's basically.
What
Yes.
happens if you double or say triple the size of your coarse graining region, if you make it bigger? Do you still see the same ellipses?
Right. So, well, we don't have much room here because, I mean, some of the systems we have 1,000 particles. We could do it in some systems we have 8,000 particles. We haven't tried that. I mean, what I would expect is that there shouldn't be a lot of change because it's known that the correlation lengths are not so huge in this kind of systems. So if you have 125 particles, you have 5 by 5 by 5, and I don't think you gain much by going to a larger system. You're just going to get smaller contours, but probably not change the anisotropy dramatically. Okay, so I think that's, I don't know, what time is it?
Yeah, it's almost an hour.
Okay, so I think I could leave it here. I guess there will be questions, so I guess I will just, yeah.
If you take a system which is time translation invariant, then you could do your statistical analysis in terms of, along the time coordinate rather than space, and this would give the same kind of contour pattern.
Well, I mean, here we have actually these two systems here, F and H, are time translation invariant. Those are in equilibrium. So I don't know if you want to do a different analysis there, if you would like to do a different.
I just mean, if your system is invariant under time translation, then correlations between 1, 2, and 3, it could be your statistical analysis could be done along the time coordinate.
You could average over the time coordinate, yes. That's so one thing that we are doing now is we are analyzing experimental data, and to basically to deal with the noise that we have, we are actually in a time translation invariant system. We are actually averaging over time. But what you need to average are the probability distributions, right? You cannot average the local correlations. You average the probability distributions, and yes, we are actually doing that. Yeah.
So if the theory that you suggest, I mean, that you can locally rescale time would be exact, but then there should be no fluctuations away from that line.
Well, right. So, but of course you do have others, yes.
Yeah. Would you expect that there is an asymptotic limit in which that could actually be observed? I mean, apparently not coarse graining size to infinity because the correlation length appears, but maybe temperature to zero, or what? Is there any asymptotic?
No, because you have the fluctuations which are associated. I mean, the simple jiggling of a particle in its cage, right? And that's totally outside of this. And that's always going to be there.
At best, you can expect that in this way of plotting things, some anisotropic ellipse, but it will never become flat.
Exactly.
I'm confused about, I mean, are you proposing a different way to think about stretched exponentials instead of just this sort of Laplace transform over different relaxation times, which I think we all agree is interesting, but not all that enlightening. Are you saying that are you suggesting that there's a different way of getting to similar results with some physical insight, or are you just saying that this is a different way of analyzing the data?
Right. So I'm not really claiming to be able to explain the stretch exponential. The use of the stretch exponential was simply to be able to analyze the data and be able to go back to describing the trajectory as a one-dimensional line. That's all. I mean, for the moment, that's all. Now, one thing that's a little bit curious here is how similar the data look in different systems. I mean, you could argue that these systems are all very similar because they are all fragile. So maybe that's the only thing that's happening there. Although it is true that you have different kinds of aging here, right? You have a different kind of aging behavior, and basically by this way of separating, right, the behavior of the global correlation into something that has to do with an initial reparametrization of the time here with those functions that I showed before, right? So by doing these fits and taking these functions h of t with different forms depending on if I had sub-aging or super-aging, basically I took out a lot of the difference between the systems and I got something that was much more similar between the systems. Now, is that a fluke or is that something that is telling me something? I don't know. Maybe there is something that has to do with, well, this h of t is describing the short-time dynamics, details of the short-time dynamics, and maybe different systems just will differ in this h of t. And a lot of what I am going to see is going to be similar to this. I don't know. That's a possible speculation.
Okay, so let's thank Horacio again.
Okay, thank you.